You're listening to DTFHN for May 7th, 2026. I'm your thermally throttled host, Jack Haxman. We are your daily tech feed for Hacker News, a website where mass extinction events get triaged by severity of technical debt. Today's a good day to own what you build. Let's get into it. Controllers are one of those problems that looks simple until you actually try to solve it. You're mapping the full range of human hand geometry. Different grip sizes, different finger lengths, different mobility constraints onto a single rigid object. And then you're asking that object to translate subtle motor intentions into precise digital inputs. The engineering is genuinely hard. The ergonomics are harder. This is why Valve releasing the full CAD files for the Steam controller matters. Not just the product renders, the actual STP and STL files, the engineering diagrams showing RF exclusion zones where you can't put material without degrading signal. This is the real geometry. You can load these into Fusion 360, into FreeCAD, into Blender, and start building. One of the comments on this story cuts right to it. Regular controllers work for people with the default number of arms, legs, and fingers. If you have a disability, you're often stuck with expensive custom solutions or nothing at all. When Valve publishes the surface topology of their controller under Creative Commons, they're handing the starting point to anyone with a 3D printer and a problem to solve. Grip extenders for smaller hands, mounting brackets for adaptive setups, smartphone clips for streaming, charging docks. Whatever the need is, the constraint is no longer access to the geometry. It's just your imagination and a slicer. Valve has done this before. Steam Deck CAD files, Valve Index files, the original Steam controller a decade ago. This is a pattern, and it's worth naming what the pattern is. A hardware company choosing, repeatedly, to give away the design surface of their products so the community can build on top of them. The README on their GitLab page reads like it was written by someone who actually wants you to use it. Friendly, clear. Here are the files. Here's what they are. Go make something now. The license is Creative Commons non-commercial, which means you can't spin up a business selling Steam controller accessories without talking to Valve first. That's a real limitation. But for the modding community, for accessibility hackers, for anyone with a printer and a use case, the commercial restriction doesn't matter. The files are there. The tools are free. The knowledge compounds. Pull this thread forward. Every hardware company that ships a product is making a choice. Do we publish the geometry, or do we lock it down? Valve keeps choosing to publish, and every time they do, someone builds something they never anticipated. That's how open source wins. Not by asking permission, but by making permission unnecessary. So, open source makes permission unnecessary. But what if your entire workday is just performing the appearance of permission-granted productivity? 50%, that's roughly the accuracy rate the Cherny et al. Stanford study found for leading language models assessing their own output. Coin flip reliability on self-evaluation. Hold that number. A careful, intelligent professional. Not an engineer. Spent 2 months building a data system using AI tools. He produced code, documentation, schemas, the full apparatus of what progress looks like from across the room. When senior engineers pointed out the architecture was wrong from day one. Wrong in ways that 2 years of formal training would have made obvious, his managers pushed back. They were too invested in the appearance of momentum to tolerate the appearance of failure. A VP weighed in. The work continued anyway. Strip this to first principles. What does a workplace actually need from a knowledge worker? 2 things. Judgment about what to build and skill to build it. Generative A, I can simulate the second without providing the first. The output looks like the output of someone who knows what they're doing. The schemas parse. the documentation reads clean. The code runs, or at least it compiles, but the objectives are wrong, and no amount of well-formatted artifacts fixes a wrong objective. The author draws a distinction worth holding on to. There are novices in a field using AI to produce work beyond their current judgment. That's one failure mode, and it's the one researchers have studied. Then there's cross-domain generation, where people produce artifacts in disciplines they were never trained in. The second is harder to detect, and in practice more dangerous, because the person generating the work cannot evaluate what they've generated, and the tool evaluating it is right about half the time. The institutional incentives are the real story. Management wants to embrace AI. Workers want to appear productive. AI makes appearing productive trivially easy. The result is a system where the feedback loop between effort and outcome gets severed, and nobody in the room is incentivized to say so. The commenters confirm this is widespread. Architects who can't explain their own architectures, requirements documents that balloon from 1 page to 12. The volume of output has increased. The signal has not. The tool isn't the problem. The tool is extraordinary. The problem is that organizations are measuring artifacts instead of understanding, and AI generates artifacts at a rate that makes the measurement gap invisible. Until a stakeholder asks a question the documentation can't answer. Moving on. What does it actually mean for data to survive? Not survive a server migration or a platform acquisition. Survive in the way that matters. 50 years, 100. The kind of timescale where the organization that created the data may not exist anymore, where the operating system it ran on is a Wikipedia entry, where the engineers who understood the format are gone. The Library of Congress thinks about this problem every single day. And in 2018, they made a quiet, remarkable decision. They added SQLite to their list of recommended storage formats for datasets. The company it keeps: CSV, JSON, and XML. That's it. 4 formats the Library of Congress trusts to carry human knowledge forward into an uncertain future. Consider what this actually means from an engineering standpoint. The criteria the LOC uses are brutally practical. Disclosure, adoption, transparency, self-documentation, external dependencies, impact of patents, and technical protection mechanisms. In plain language, can someone understand this format with no help, no license, no proprietary tool, no internet connection, and no prior knowledge of who made it? SQLite passes every one of those tests, and the reason is architectural. The entire database is a single cross-platform file. The format is documented down to the byte. The source code is in the public domain. Not MIT, not Apache, not GPL. Public domain. Richard Hipp made a deliberate choice to remove every possible friction point between his work and the future. There's a parallel worth naming. In 1985, the PostScript language specification was published as a book. Adobe could have kept it proprietary, but they documented the format so thoroughly that anyone could write an interpreter. That decision is why we can still open documents from 1987. The format outlived the market dominance of the company that created it because the specification was truly open. SQLite takes this further. PostScript was documented but copyrighted. SQLite is documented and free. The code is the specification, and the specification belongs to everyone. One commenter captured the real trajectory perfectly, going from dismissing SQLite as a toy to using it for almost everything. That's the journey. The engineering is so quietly excellent that it takes time to appreciate what's actually been accomplished. a database engine used on literally billions of devices, trusted by the institution whose entire mission is making sure humanity's knowledge doesn't disappear. The tools exist. The format is open. The blueprints belong to no one and everyone. This is what preservation looks like when engineering serves permanence instead of profit. Now, if that was about making software last forever, this next story asks a much wilder question. What if the hardware could too? One commenter on this thread said something that stuck with me. They argued permacomputing is the missing piece of the free software movement, because what use is free software long-term if you don't have hardware you can control, maintain, and repair? That's not a hypothetical. That's a diagnosis. Think of it like soil science. In industrial agriculture, you optimize for yield per season. You deplete the topsoil, pump in synthetic inputs, and when the land gives out, you move on. Permaculture inverts this. You optimize for yield per century, you build soil, you close loops, you treat the substrate as the product. Permacomputing applies the same inversion to silicon. The chip is the topsoil. Every microprocessor begins as sand, passes through the most resource-intensive manufacturing process humans have ever devised, and ends up in a landfill 18 months later because someone decided the bezels should be thinner. The permacomputing argument is simple. What if we optimize for yield per century instead of yield per quarter? Now, some commenters push back. One called it misplaced post-collapse resiliency, solving hypothetical problems. And honestly, the deadpan comedy here is that we already live in the collapse scenario for most of the planet. E-waste is not hypothetical in a block splash. Supply chain fragility is not hypothetical when one ship blocks one canal and your chip delivery slides 6 months. The unintended consequence of treating hardware as disposable is that you've built civilization on a substrate you cannot reproduce locally, cannot repair locally, and cannot even understand locally. The permacomputing response isn't degrowth dressed as engineering. It's the recognition that resilient systems and open systems converge. If your software runs on decade-old hardware, it runs everywhere. If your protocols assume intermittent connectivity, they work in a mesh network or a submarine or rural Appalachia. Constraints breed universality. What I find genuinely exciting is the builder energy here. People in Berlin running meetups. Communities growing their own compute infrastructure. This is Tankera culture applied to the full stack. Not just the code, but the atoms underneath it. The principle isn't prepare for apocalypse. It's design as if materials matter, because they do, and the engineering gets more interesting when you acknowledge that. Creativity thrives on constraints. Always has. We talked about stripping things down to essentials. Pause now, someone's taken that literally and booted Linux without a hard drive. I've mass deployed hundreds of machines in my time, and the thing that always stuck with me about PXE boot isn't the network protocol itself. It's the moment you realize your operating system doesn't need to live where you use it. That separation of compute from storage, once you internalize it, changes how you think about every machine you touch. This post by Anikit is a beautiful example. The setup is practical and honestly kind of funny in its motivation. Gaming PC full of NVMe drives loaded with games. Windows install barely holding together under layers of toolchain. Python Minga Code WSL. The person just wants to run some local LLM inference with the new onslaught, quantized models, and doesn't want to fight Windows to do it. Class A. The solution is gorgeous in its indirection. Instead of dual booting and risking Windows breaking grub on every update, instead of burning yet another USB drive destined to be reformatted at a FedEx counter, The entire Linux installation lives on a ZFS, ZVol, exported as an iSCSI target from an existing Proxmox server. The gaming PC boots over PXE, picks up its root file SLI from the network, and runs Debian entirely from remote storage. Grub itself lives on the remote drive. No local bootloader to maintain at all. Now run this forward. Imagine every machine in your house boots this way. Your NAS holds a ZFS pool of operating system volumes, each one independently snapshotable, clonable, rollbackable. You brick and install experimenting with some bleeding edge driver. Roll back the snapshot in seconds. You want the same development environment on 3 different machines. Clone the ZVol. The file system becomes infrastructure, not a local artifact bound to whatever disk happens to be in the chassis. The technical stack here deserves appreciation. netboot.xyz compiled locally so it doesn't pull assets at runtime. IPXE chain loading into an iSCSI initiator. DNS mask on a Merlin firmware router handing out the boot server address. ZFS underneath providing the storage semantics that make this whole architecture worth the effort. Every layer is open, every component is replaceable, and the whole thing runs on commodity hardware the author already owned. One commenter nailed something important. iSCSI gets unhappy on congested networks with packet loss from incast traffic. GOS, tuning matters here. That's real operational knowledge. The kind you only get from running these systems under load. Another pointed out that refined eliminates the grub maintenance headache entirely. The comments are doing what they should. Sharpening the engineering. This is tinkerer infrastructure at its best. One person, one weekend, open tools, and suddenly a gaming PC becomes a thin client that boots a snapshotable Linux environment from the network. The tools exist. Every piece of this has been open for years. The only thing required is the willingness to wire it together. Now sometimes the willingness to wire things together hits a wall, and that wall is called Photoshop. In Untitled the original Macintosh with a document called the Human Interface Guidelines, it wasn't a suggestion. It was a contract with the user. If you build software for this platform, focus states work consistently, tab order is predictable, selected text highlights when you click into a field. These weren't radical ideas, they were the baseline, the floor beneath which no shipping product should fall. 42 years later, Adobe has released Photoshop 2026 with input fields that don't focus when you open a dialog. Fields that don't select their contents when you click into them. A backspace key that triggers an error modal, and then... Genuinely incredible design decision here. Removes focus from the field you were typing in. Tab order that routes you through drop-down menus instead of the next input. Ignoring macOS's own keyboard navigation preferences. Undo keystrokes swallowed by UI elements that have no idea what to do with them. Marcin Witchery's teardown is methodical and damning. Every issue he catalogs traces back to the same root failure. Focus management, the most fundamental contract between an interface and a human being. When you open a dialog to resize a canvas, you should be able to type a number. When you click a field, its contents should select. When you press Tab, you should land somewhere useful. These are principles from the 1980s. They are not ambiguous. And here's where architecture tells the story. Adobe rebuilt these dialogues in their Spectrum design system. A ground-up re-implementation of Interface Chrome that managed to lose decades of accumulated interaction correctness. One commenter points out they've rolled back to the 2020 version because it actually works. Another has used Photoshop for 30 years and watched it degrade from favorite software to daily frustration. This is what happens inside a closed system when the objective function drifts. Adobe doesn't need these dialogues to be good. They need them to be modern. They need a design system that looks unified in a pitch deck. The people spending 8 hours a day in these windows have no recourse, no fork, no alternative implementation. The subscription model ensures you receive the update whether you wanted it or not. Meanwhile, GIMP, Krita, Photopea. Projects built by people who actually use image editors. Keep grinding forward. They ship focus states that work because the developers feel the pain of focus states that don't. The tools exist. They're getting better every year. And nobody can enchitify them with a quarterly redesign mandate. Moving on. The strongest argument against calculator programming as meaningful computer science education is that it was accidental. No curriculum designer intended for bored 15-year-olds to discover for loops on a graphing calculator. The hardware was closed. Texas Instruments never open-sourced the operating system. The language was primitive. No functions as first-class objects. No recursion worth speaking of. Brutally limited memory. By any reasonable pedagogical standard, Italian Basic was a terrible first language taught in a terrible environment by no one at all. With all of that logic to its conclusion, if legitimate programming education requires a designed curriculum, proper tooling, a credentialed instructor, and an explicitly open platform, then the thousands of working software engineers who trace their origin story to a TIA3 in algebra class shouldn't exist. But they do. Boris Cherny wrote this tutorial in 2004 when he was a teenager for other teenagers, and it found its audience because the need was real and immediate. This is what matters about the story. The TIA3 was a closed system that accidentally produced an open result. Texas Instruments sold you a locked-down device for 300% markup, but they couldn't prevent a kid from typing program on it. They couldn't stop that kid from showing the kid sitting next to them. They couldn't prevent Boris Cherny from writing it down and putting it on tcalixchic.org, where it would outlive every corporate initiative TI ever launched around education technology. The Tomans confirm what anyone who lived through this already knows. The TIA3 was arguably the most effective unintentional programming education platform ever built. One commenter notes the original manual itself was enough. Another wrote their own tutorial in German that became the most read thing on their blog. The knowledge replicated because people wanted it, and nothing stood in the way of sharing it. The lesson is architectural. You cannot prevent humans from programming a programmable device. You cannot prevent them from teaching each other. The entire formal education technology industry, billions in venture funding, learning management systems, credentialing platforms, has never matched the conversion rate of a bored sophomore with a graphing calculator and 20 minutes before the bell rings. The tools exist. Sometimes they exist by accident. The builders find them anyway. Moving on. Simon Willison uses the word guilt, not concern, not caution. Guilt. That word choice matters more than anything else in his essay. He's describing a specific situation. He asks Claude Code to build a JSON API endpoint. It writes the SQL query, outputs JSON, adds tests, adds documentation. He knows it's correct. He's seen it do this correctly hundreds of times. But he hasn't read every line. And that feeling, that specific guilt, is what he's grappling with. Here's where it's worth playing devil's advocate against Willison's own framing. He treats the convergence of vibe coding and agentic engineering as disturbing. A blurring of a line he thought was firm. But consider the alternative he himself raises. When he managed engineering teams, other teams shipped services his team depended on. He never read their code. He read their docs, tested their APIs, filed bugs when things broke. Nobody called that irresponsible. Nobody called that vibe management. The distinction he's mourning may never have been real. What separates a professional from an amateur has never been reading every line. It's knowing which lines to read. It's understanding failure modes. It's having the judgment to know when something needs scrutiny and when it doesn't. A senior engineer reviewing a junior's pull request doesn't read every line with equal attention. They pattern match. They check the boundaries, the error handling, the security surface. They skim the straightforward parts. That's not negligence. That's expertise. One commenter cuts to the real issue. The errors aren't gone. They're more subtle now. Code that compiles and passes tests but has a logic flaw 3 layers deep. That's a legitimate concern. But it's also been the concern with every abstraction layer ever introduced. Nobody reads the assembly their compiler generates. Nobody audits the kernel syscalls their framework invokes. The interesting number in this conversation is the one another commenter flags. 200 lines of code a day to 2,000. If the entire software development lifecycle was designed around human output rates, then the tooling, the review processes, the deployment cadences all need to change. Not because the code is worse, because the bottleneck moo. Willens' guilt is honest, but guilt is not analysis. The question isn't whether you read every line. It's whether you built the systems. Tests, monitoring, architecture. That catch what your eyes would have caught. Engineering was never about reading. It was about knowing. Moving on. The small block Chevy is arguably the most important engine in American hot rod history. Millions of them. Standardized mounts. A parts ecosystem so deep you could build one from a catalog without a single OEM component. The whole point of a crate motor is that you buy it, you drop it in, you wire it up in your garage on a Saturday. That's the contract. That's what crate means. Chevrolet's eCrate package is a 400-volt, 200-horsepower electric drive unit with battery modules, and on paper, it's a genuinely interesting proposition. Take a classic body gut the drivetrain, go electric, the engineering is real. 200 horsepower with instant torque in a vintage Blazer or a 67 C10 sounds legitimately fun to drive, and the charging story is reasonable. Level 2 gets you 10% an hour. DC fast charging gets you 75%. For a weekend cruiser, that's more than enough. But there's a question nobody at GM seems to want to answer. What exactly makes this a crate motor? $27,000. Professional installation required for the charger. And the deeper you dig into GM's connected vehicle architecture, the more you realize this isn't a powertrain you own the way you owned a small block. One commenter put it bluntly. It's a crate motor you can't install yourself. Another pointed out the privacy implications of GM's telemetry stack, which has already been caught selling driver behavior data to insurance companies. The original small block succeeded because it was legible. A teenager with a Chilton manual could understand every system, could modify it, could break it and fix it, and make it faster. The knowledge was transferable. The parts were interchangeable. It was open architecture before anyone called it that. The eCrate could have been that for the electric era. An open, documented, hackable electric powertrain that invited the hot rod community to do what they've always done. Build. Instead, it's a sealed unit from a company that treats post-sale data extraction as a revenue stream. The motor is probably excellent, The engineering team probably cares deeply about this product, but the institution wrapped around it has different objectives than the people in the garage. The crate is closed, and a closed crate is just a box. Closed boxes, closed ecosystems. Turns out the open web has been quietly winning one battle this whole time, and RSS is the proof. 25%. A quarter of all traffic to a personal blog comes from people who deliberately, voluntarily subscribe to an RSS feed. More than Google sends. Let that land for a moment. Not because it's shocking, but because of what it reveals about the architecture of attention on the web. Terence Eden ran the numbers on his blog. Lightweight local-only analytics. No creepy tracking, no ad network surveillance, just the rough count of where readers come from. Google's up there, sure. DuckDuckGo makes a respectable showing. Bing barely cracks the top 20, which sounds about right. But RSS and email newsletters? They're beating the world's dominant search engine. Now, the selection bias is real, and the comments are quick to flag it. Eden writes about open web standards. His audience skews toward people who actually use feed readers. Data point of 1, absolutely. But the pattern keeps showing up. Susan Paul reported the same thing. Other bloggers in the comments are seeing RSS account for up to 70% of their server traffic. This isn't an anomaly, it's a signal. RSS is a protocol from 1999 that nobody owns. There's no algorithm deciding what you see, no engagement metrics throttling reach, no advertising auction between the writer and the reader. You publish, subscribers receive. That's it. The entire transaction is legible, predictable, and free. Every few years someone declares RSS dead, and every few years the people actually building and reading on the open web just keep using it. Google killed Google Reader in 2013, and the ecosystem didn't collapse. It diversified. Tiny reader apps, self-hosted solutions, people wiring up LLM agents to triage their feeds. The protocol survived because no single company controlled it. There was no off switch to flip. The interesting detail in Eden's post isn't the numbers. It's that he describes his subscribers with the word chosen. These people chose to show up. No algorithm herded them. No dark pattern nudged them. They found something worth reading, and they built their own pipeline to keep getting it. That's what an open protocol makes possible. A relationship between writer and reader that no platform mediates, no corporation monetizes, and no policy change can break. This has been your daily tech feed for Hacker News for May 7th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that belongs to you. We'll see you back here tomorrow.